Welcome to today's deep dive. We are looking at a highly speculative, conceptually aggressive preprint that's archived on Zenodo right now.
Yeah, conceptually aggressive is definitely the right phrase for it.
Right. It's titled The A Model, Unification of Matter, Consciousness, and the Vibrational Field by Jesus Eduardo Jimenez de la Garza. And just to set the stage for you listening, our focus here today is exclusively on the formal mathematical architecture that the author proposes.
Exactly, because it's a fascinating framework. We're examining how he uses, differential geometry, topology, and dynamical systems theory to ask a really profound question about the structural layer of reality itself.
But before we get too far into the weeds, I think it's essential to establish the parameters here right away.
Oh, absolutely. I mean, this is very much a theoretical exercise. It's an invitation to explore a specific mathematical language, one that attempts to map out how stable structures might emerge from a continuous interacting field.
So we're definitely not discussing empirically validated findings from the Large Hadron Collider here.
No, not at all. We are engaging with a rigorously structured hypothesis about phase synchronization and complex systems. It's a theoretical sandbox, really.
Which honestly makes it the perfect candidate for a deep dive. Because the implications of the math, they kind of force you to completely reevaluate the tactile nature of everyday objects.
They really do. It completely subverts your intuition.
Think about just picking up a rock.
Mhm.
Classical mechanics, and honestly just our basic sensory perception, trains us to assume we are holding a localized solid mass.
Right, you feel the weight, the texture. It feels undeniably solid.
Exactly. We carry this ingrained assumption that if you zoom in far enough, you eventually hit a fundamental static brick of reality. A tiny, unbreakable piece of matter.
And, the persistence of that localized particle view is powerful because it works so well for standard macroscopic engineering. But when you look at certain contemporary theoretical frameworks, and particularly the model proposed in this paper, that discrete billiard ball image of matter is just entirely discarded.
It's thrown out the window.
Completely. It is replaced by something inherently fluid. The proposition here is that the rock isn't a collection of minuscule solid things. It's a highly persistent emergent pattern of relational dynamics.
Emergent pattern, okay. To even entertain that idea, the paper requires us to strip away the concept of an empty vacuum acting as a container for objects, right?
Yes. The author introduces what he calls the A field. So we aren't looking at discrete actors moving across an inert stage. The stage itself is the active medium.
The stage is alive, basically.
Basically, yeah. Everything we perceive as physical matter is just a localized, organized fluctuation within this continuous dynamical field.
And that shift in ontology, that brings us to one of the central mathematical axioms of the text, which is the relational primacy of phase.
Which is a huge departure from standard physics. I mean, in a lot of classical physics, absolute values drive the equations. You isolate a particle and measure its absolute position, its momentum, its energy.
But the A framework flips that hierarchy entirely.
It does. The absolute state of a single isolated point is mathematically secondary here. The primary driver of physical structure is its phase relationship with the local environment.
It's essentially treating the foundation of reality like an infinitely complex signal processing problem,
That's actually a really good way to think about it.
Right, because in signal theory, absolute amplitude isn't what gives a transmission its structure.
Yeah.
The information is encoded in the relative phase alignment.
Exactly. If you have a multitude of signals transmitting with massive energy but completely misaligned phases, all you get is destructive interference.
Just pure noise.
Pure noise. The structure, the data, really only emerges when the relative timing locks in perfectly.
Building on that signal processing framework, the mathematics here formalize that exact intuition. The model argues that the emergence of stable physical matter is entirely dependent on that phase alignment.
Yes. If a localized region of the field achieves a specific relational synchrony, it produces what we observe as interactive matter.
And if the phase relationship is uncoordinated?
Then it remains a disordered, unobservable background state, just part of the fluctuating field.
But logically, if the defining characteristic of physical mass is just relative timing within a continuous fluid medium, that structural integrity should be incredibly fragile.
You would think so, yes.
I mean, a rock doesn't spontaneously desynchronize and dissolve into background noise just because I drop it or, introduce thermal energy by heating it up. How does the model account for the stability of these phase relationships?
Well, the framework addresses that fragility by introducing a rigorous quantitative duality, coherence, and phase entropy.
Okay, break those down for us.
Sure. In this model, coherence isn't used as just a qualitative descriptor. It is formulated as a specific functional that measures the degree of phase alignment across the system at any given moment.
So it's essentially a strict mathematical metric for the structural order of the field.
Precisely. And its mathematical counterweight is phase entropy, which measures the dispersion or the variance of those phase relationships.
Almost like thermal entropy in thermodynamics.
Very much so. It's constantly pushing the system toward disorder. So the stability of any physical structure in this framework is dictated by a constant dynamic tension between these two values.
Which means there has to be a critical threshold, right? If the coherence drops below a certain mathematical limit, the phase entropy overwhelms the system and the structure just dissipates back into the field.
Yeah, the paper defines this explicitly as the stability threshold. Not all configurations of the field can survive. And what is conceptually fascinating here is how this threshold affects the geometry of the conceptual space itself.
How so?
Well, the mathematics suggests that areas of high phase coherence actively warp the local mathematical topography. They create what you can think of as valleys of stability.
Like an energy landscape where falling into the valley is just mathematically favorable.
Exactly the concept. Once a localized region of the field achieves enough coherence to cross that stability threshold, it settles into one of these valleys.
And it stays there.
Right. The structure becomes robust because maintaining its form requires less energy than climbing out of the valley into a state of high entropy. Regions dominated by phase entropy, on the other hand, are geometrically unstable. They're like steep gradients where no pattern can persist.
Okay, so that answers why a structure stays together once it's already formed. But it leaves a massive causal gap.
The initiation problem.
Right. If we have a highly entropic, continuous field of varying phases, what initiates the climb out of disorder in the first place? Standard physics relies on external forces or thermal fluctuations to drive phase transitions. What is the internal mechanism here that drives a completely noisy field to spontaneously coordinate and find that valley?
To solve the problem of spontaneous coordination, the author integrates the mathematics of coupled oscillators, specifically relying on Kuramoto models.
The Kuramoto model.
Yep.
That's typically used for things like the spontaneous synchronization of firing neurons or power grids, right? Dealing with massive networks of nonlinear oscillators.
Yes, it is one of the most elegant mathematical descriptions of collective synchronization we have. The Kuramoto model describes a system of independent oscillators where each possesses its own intrinsic natural frequency.
So left to their own devices, they just do their own thing.
Exactly. Their phases diverge, and the phase entropy of the system remains high. But the critical element is nonlinear coupling.
But in the context of a continuous field, what exactly constitutes the coupling? I mean, we aren't dealing with physical wires connecting nodes on a grid.
No, in the E field, you can conceptualize localized fluctuations as the nodes. Because the field is continuous, any perturbation in the phase of one localized region inherently influences the boundary of its immediate neighbors.
Oh, I see. They can essentially feel the phase evolution adjacent to them.
Right, and the Kuramoto model demonstrates that this interaction strength, the coupling parameter, dictates the behavior of the entire system.
And as that coupling parameter increases and approaches a critical value, you trigger a global phase transition.
And the transition is abrupt, and it's mathematically beautiful. The collective alignment is measured by something called the order parameter, which scales from 0 to 1.
Okay, 0 being noise, 1 being perfect order.
Exactly. At a low coupling strength, the order parameter hovers near 0 pure noise, high entropy. But the moment the coupling strength crosses the critical threshold, small, localized pockets of synchronization begin to recruit surrounding fluctuations.
It's like a domino effect.
Very much like that. The order parameter spikes toward unity. Macroscopic numbers of oscillators spontaneously lock into a shared collective phase evolution.
So in the language of this theoretical framework, the genesis of matter is simply a localized region of the E field undergoing a Kuramoto phase transition.
That's the idea, yes.
The field's internal coupling reaches a state where it forces the local phase entropy to plummet, the coherence spikes, the order parameter nears 1, and the region drops into a valley of stability. The rock I'm holding is just a localized pocket of the universe that is violently resisting desynchronization.
That is the mechanical core of the hypothesis. Mass and the tactile resistance you feel is reinterpreted as the inertial resistance of a highly synchronized region to external phase disruption.
That is wild. But it presents a major problem for standard Hamiltonian mechanics, though.
It definitely does.
Because if Physical objects are essentially vast, delicate networks of coupled oscillators locked in a shared phase. Moving that object through space, or having it interact with another object, should shatter the synchronization. Standard Hamiltonians generally deal with pairwise interactions, right?
Right, like a force acting on a momentum or a particle interacting with a potential.
Yeah. If you apply a binary interaction to a field where phase, coherence, and entropy are so deeply interdependent, the global structure would just collapse under the perturbation.
Which is exactly why standard Hamiltonian formalism is insufficient for the A model. The pairwise interactions you mentioned simply cannot maintain the global topological stability required for the synchronized state to survive over time.
So what's the alternative?
To resolve this, the paper abandons the classical Hamiltonian approach entirely and utilizes Nambu dynamics.
Yoichiro Nambu's generalized mechanics.
Yes. Nambu proposed a mathematical extension of Hamiltonian mechanics. Instead of a single generating function dictating the evolution of a system through two variables like position and momentum, Nambu mechanics operates through ternary or triadic structures.
Triadic structures, meaning 3 variables instead of 2.
Exactly. It employs Nambu brackets, which allow 3 independent variables to simultaneously govern the dynamical flow of the system.
So instead of a 2-dimensional phase space flow, we are dealing with an intertwined 3-dimensional mathematical engine. In the context of this field, what are the 3 variables driving those Nambu brackets?
The triadic engine is constructed precisely from the properties we've been discussing: phase, coherence, and entropy.
Okay, that makes perfect sense.
The Nambu brackets formalize an internal rotational flow where these 3 values continuously and simultaneously adjust to one another.
It's a self-correcting feedback loop at a fundamental level. You literally cannot perturb the phase of the field without the Nambu engine instantly recalculating and shifting the local coherence and the local entropy to compensate.
And the structural brilliance of applying Nambu dynamics here lies in a property analogous to Liouville's theorem in classical mechanics. The Nambu brackets inherently preserve the volume of the phase space as the system evolves.
Let's define that conservation for the listener really quick. Preserving the phase space volume means that the total informational and structural integrity of that synchronized region doesn't just, compress into a singularity or infinitely expand to pure variance.
Precisely. It provides a mathematical guarantee of global stability across multiple scales. As the synchronized Kuromoto region moves, interacts, or faces external perturbations, the forces are instantly distributed across the triad.
Right.
If external noise threatens to increase the phase entropy, the Nambu dynamics force a corresponding shift in phase and coherence to preserve that structural volume.
So basically, theoretical physicists have mathematically formulated a universe where my coffee mug is governed by a deeply entangled, 3-way dynamical seesaw that just refuses to let the object fall apart.
It's a vivid image, but yes. It is a mathematically robust way to explain the durability of matter in a universe that is fundamentally constructed out of vibrations. The triadic Nambu engine acts as the preservation mechanism for the Kuromoto synchronization.
But there's still a missing piece here, I feel like.
What's that?
Well, the Kuromoto model gets the field to synchronize, and the Nambu engine keeps it from falling apart under pressure. But a rock, or an electron, or a coffee mug has a specific geometric identity. It has boundaries.
I see where you're going.
It has properties that distinguish it from other synchronized regions. How does this endless fluid math suddenly generate a defined edge and a distinct identity?
To bridge the gap between a continuous synchronized field and the discrete, bounded physical objects we actually interact with, the paper introduces its final major concept, which is topological persistence and the formation of reality knots.
Okay, topology. That's the study of properties that are preserved under continuous deformation, stretching, twisting, bending, but not tearing or gluing, right?
It's a perfect summary. And it is the ideal mathematical tool for this framework. When the triadic Nambu engine successfully maintains a high coherent state over an extended period, the phase organization doesn't just sit statically.
It moves.
Right. The dynamical flow can actually wrap around itself, creating a non-trivial topological structure in the field.
A topological defect, essentially, like magnetic flux tubes in a plasma or vortex lines in a superfluid.
A highly accurate comparison. In the paper's terminology, these are reality knots, and the defining characteristic of a topological knot is its incredible durability.
Because it's knotted into the field itself.
Exactly. You can stretch a knot, compress it, dynamically deform its geometry, and change its spatial coordinates entirely. But as long as you do not sever the fundamental continuous connections, which in this model means as long as the coherence doesn't drop below the critical stability threshold, the knot cannot be undone.
The identity of the object is entirely tied to its topological invariance, not its material constituents.
And that is the core philosophical shift of the paper. The underlying E field is in constant flux. The material making up the region is continuously flowing and changing, but the specific knotted shape of the synchronized phase persists.
It fundamentally redefines what an object is. An object is not a thing. It is a persistent topological behavior of a medium.
Yes. We interact with the stable topology, not the transient medium. All discrete physical structures, electrons, molecules, rocks, are interpreted as these highly stable, topologically knotted whirlpools in the continuous flow of the field.
The phase rotates, the medium changes, but the knotted structure persists, shielded by that triadic balance of Nambu dynamics.
Exactly.
Taking a step back, the architectural rigor of this hypothesis is really remarkable. We started by discarding the vacuum and replacing it with the continuous A field. Then we explored how random phase noise can cross a stability threshold through Kuromoto synchronization. We saw how standard Hamiltonian mechanics fails to protect that synchronization, requiring the complex, volume-preserving triad of Nambu dynamics.
And finally, we arrive at the physical world we know through the emergence of persistent reality knots.
It is a highly cohesive synthesis of complex systems theory, generalized dynamics, and topology. And approaching reality from this perspective forces us to consider the boundary conditions of our universe in a completely different light.
It really does. The mathematics dictate that the existence of stable geometry and physical mass is entirely contingent on maintaining that specific regime of phase coherence.
Which means there must be extreme environments where the Nambu engine fails to preserve the phase space volume.
And the implications for the extremes of astrophysics there are profound. Consider the interior of a black hole near the singularity or the outer edges of cosmic inflation.
Places where the rules break down.
Right. If you expose a topological knot to an environment where the phase entropy is so overwhelmingly massive that it forces the coupling parameter below the critical threshold,
The order parameter collapses back towards zero.
and the topological knot unties. In those extremes, the framework suggests that matter doesn't just get crushed or compressed into a denser physical state. The very concept of physical form ceases to exist.
Wow.
The synchronization breaks, and the matter simply dissolves back into the raw, unstructured phase noise of the fundamental field.
It is a stark reminder that the solidity we rely on every day might just be a localized mathematical anomaly. The next time you feel the weight of a rock in your hand, consider that it might not be a permanent fixture of reality. It might just be a stubborn topological knot of synchronized math, temporarily holding its own against the entropy of the universe. Something for you to ponder.